Okay, so we saw in our flip class video on optimization how our work on maximums and minimums could be applied in a real world situation that was involving economics. So for this regular lecture video, we're going to see several more applications of max and mins and optimization problems with word problems. So let's go ahead and just get going on some examples. There's going to be lots of different types of examples here. Okay, so our setup here is we have a warehouse that's going to be selling some product. They need to determine how often and what quantity they're going to make their orders. So it is cheaper on average to place large orders as this reduces the ordering cost per unit. On the other hand, larger orders means we have to pay to store. Okay, so the warehouse always orders or always reorders the product in the same quantity. So that means we're not going to order a certain amount one time and then change the amount of order the next time. Okay, so our cost for ordering and storing our products, if we order Q of them, is given by C of Q, which is A over Q plus B over Q. A and B here are positive constants. So we're going to answer several questions about this setup. So let's look at the first one. Let's try to actually understand what this equation is telling us. So if we look at the two terms that make up our C of Q, which does each correspond to? So which represents the ordering cost and which represents the shipping costs? So the way we want to think about this is we know that the more we order, the larger the shipping cost, and the more we order, the smaller the ordering cost. So if we look at each of these terms, A over Q, so let's take A over Q here, and BQ. So as Q gets large, A is a positive constant, so this gets small. And this gets large as Q gets large. So that means this one should be the storage, because we know the storage cost gets large as Q gets large, and we know that the ordering cost gets small as Q gets large, so this should be the ordering cost. So that's how we understand those two terms in the equation. That's our first step. Now let's look at what value of Q gives the minimum total cost. So for this, what we're looking for are critical values. So we want the critical values. Of C of Q. So that means we need to take the derivative. So C prime of Q is going to be minus A over Q squared plus B. Now we know this, the critical numbers would be where this is 0 or undefined. Would be undefined where Q is equal to 0, but clearly we need to make an order, so we don't want to worry about that. So we want where C prime of Q is equal to 0. So that's going to be when minus A over Q squared plus B is equal to 0. And so this is the same as B is equal to A over Q squared, which is the same thing as Q squared is equal to A over B. So that tells me then that Q should be plus or minus the square root of A over B. But of course, Q is a quantity of something we're ordering, so it needs to be positive. So we want Q to be bigger than 0. So our critical number is Q is equal to square root of A over B. And now we want to make sure that this actually gives us a minimum, so we look at the second derivative. So if we look at that, that's just A over Q cubed. So if we evaluate this at our critical number, this is A over B to the 3 halves, which is positive. So think of it like this. So this gives a minimum. So this value of Q over equals square root of A over B gives the minimum. So that's how many we should order to minimize our cost. Okay, so let's try another example. Okay, so our potential energy of a particle moving along the x-axis is given by U of x is equal to B times A squared over x squared minus A over x, where A and B are positive constants, and we want x to be bigger than 0. So what value of x minimizes the potential energy? So once again, we're looking for critical numbers here. So let's take the derivative. This b is a constant, so that just stays where it is. I'm going to get minus 2a squared over x cubed plus a over x squared. So notice I can factor an a over x squared out, so I'll have ab over x squared. And then if I factor out, I get 1 minus 2a over x. Now remember, we've assumed that x is bigger than 0 here, so our critical numbers, well, normally we would have x equals 0 because that's a spot where this is undefined, but we have x bigger than 0 here, so that doesn't happen. So this is when u prime of x is equal to 0 for this case. And this can, the a and b are positive constants, so this can only happen when 1 minus 2a over x is equal to 0. So this is the same as 1 is equal to 2a over x, or x is equal to 2a. So that's our critical number. And now we want to check and make sure this is actually a minimum. So we take the second derivative. So if we look above at this term here and we take the second derivative of this, the b will stay the same. And I'm going to get 6a squared over x to the fourth minus 2a over x cubed. And so when I plug in the 2a to this, I get b, and then I get 2a squared over 2a to the fourth minus 2a over 2a cubed. Oh, this should be 6. Sorry, that should be a 6. This should be a 6 here. And so if we simplify this, this becomes b over 4a squared times 1/2, which is bigger than 0. So the critical number x is equal to 2a gives the minimum that we were looking for. Okay, let's try one that's a little bit more involved now. Okay, so you're going towards the bus stop. You see the bus approaching. You need to figure out how to get to the bus stop as fast as possible. Okay, so we know that the bus stop is across the other side of a grassy park. So it's 1,000 feet west of you and 500 feet north of your position. That's the size of the park as well. Basically, you're on one corner of the park and the bus is on the other. So you can Okay, so if you stay outside of the grass, you can walk at 5 feet per second. However, once you're in the grass, you can only walk 3 feet per second. Okay, so what path gets us there the fastest? Okay, so we can think about this. Obviously, we're going to want to take straight lines because those minimize our distance traveled. So suppose you're here and the stop is over here. Now, what we can do is if we were to run, we could run or walk some distance this way and then go across the park some distance and then go across like this. So say this is like distance A, B, and C. So one thing to note here is we could also, if we're just talking about how long it takes, the time it takes to run this path that I drew first is the same as if I were to run this path like this. If this is B and this is A plus C, those take the same amount of time because you have A plus C amount of time on the sidewalk and B time in the grass. So we might as well just look at the second setup for our picture here. So let's do that setup, but let's relabel these things. So let's say here's the stop. You're over here. And let's say you're going to run a distance, or run or walk a distance x here, and then this distance here is going to be y. Now we know that the distance is equal to the rate times time. So that means time is equal to the distance divided by the rate. So our total time here would be the distance traveled on the sidewalk, x, divided by the rate you can run on the sidewalk, plus the distance traveled in the grass, divided by the rate you can run in the grass. So this would be our equation here for the total time taken. And now we want to use the fact here, we want to figure out how to get rid of one of those variables. So note that this whole distance here is 1,000. So that means this distance is 1,000 minus x. And we know this distance here is 500. So that tells me y squared is equal to 500 squared plus 1,000 minus x squared. Or y is equal to the square root of 500 squared plus 1,000 minus x squared. So I can rewrite the time then, now as just a function of x, is x over 5 plus, and then I'm going to have 1/3, and then I have the square root of 500 squared plus 1,000 minus x squared. And that's my function for the time it takes to get from the part you are to the bus stop along this path. And we want to minimize this. So it's really helpful to draw these pictures like we've done here to help us understand what's going on and to get the right equations. Okay, so if we're going to minimize t, we need to take its derivative and find the critical points. So the derivative of the first term there is just going to be 1/5. And now for the second term, we're going to have to use chain rule. So I'm going to bring down the 1/2 from this. And I'm going to get a 1/6. And then what I'll have left over is I'll have the 500 squared plus 1,000 minus x squared. And then this will become a negative 1/2. And now I need to take the derivative of what's inside, which is going to be a 2, 1,000 minus x, and then times the derivative of that, which is minus 1. So we can simplify. Sorry, not sure what happened. Okay, so we can simplify this a bit. So this 2 will cancel with the 1/6 to give me a 1/3. So I'll have 1/5, and I have that negative, so I'll have minus 1/3. And then I have a 1,000 minus x in the top, and then I have 500 squared plus 1,000 minus x squared to the 1/2 in the denominator. So we can see then that we have t prime of x is equal to 0 when we'll set this equal to 0. I would have 1/5 is equal to 1/3, 1,000 minus x over 500 squared plus 1,000 minus x squared to the 1/2. Now I can square both sides. We'll bring the 3 over and square both sides, and I'll have 9 over 25. And on the other side, I'll have a 1,000 minus x squared. And if I square the denominator, that just gets rid of the square root. So now let's clear the denominators out. And so I'm going to have 9 over 25. And I'm going to have 500 squared plus 9 over 25, 1,000 minus x squared equals 1,000 minus x squared. So bring that 9/25 over to the other side. And I'll have 9 over 25 times 500 squared is equal to, And so if I subtract it, I'll have 16 over 25 times 1,000 minus x squared. Now I can cancel those 25s and divide through by the 16. And so I can rewrite this as 500 times 3 over 4, the entire thing squared. That's that 3 over 4 squared, that's a 9 over 16, is equal to 1,000 minus x squared. So I can take square roots of both sides, and then I'm going to have 500 times 3 over 4 equals 1,000 minus x. And so I want to then solve this for x. So x is equal to 1,000 minus 1,500 over 4. So this is 4,000 minus 1,500 over 4. So this gives me 625. So that's our critical number. So you can see that was a lot of work to figure out what that critical number was, but it was the same process as we always do. We find the equation, we take the derivative, and we solve for when that thing is equal to 0. Now finally, we need to check that this actually gives a minimum. So that means we need a second derivative, so that's going to be even messier. So if we do that, notice the first term here of our derivative, when we go way back up here, this 1/5 will go away because that's a constant. So I'll have a negative 1/3, and I'm going to have a big old mess in here. So I'm going to use quotient rule. So that's just using the quotient rule there. And now if we plug our critical number of 625 in and do a bunch of simplification, this becomes 1/3 625 minus 375 squared over 625 all over 500 squared plus 375 squared, and this is bigger than 0. So x equals 625 gives the minimum. And then of course, if you wanted the path, we would know if we run x distance on the, so we run, so we'll say walk, I think is how it's phrased, 625 feet on the sidewalk, then run diagonally to the bus stop. And that would minimize the amount of time it takes to get to the bus stop. Okay, let's do another one that's not quite so involved as that one, but does illustrate some important techniques to use in some optimization problems. Okay, so we have a hemisphere of some fixed radius r sitting on a horizontal plane. Let's say with this. Okay, so we have a cylinder that's going to have its axis going vertical and its base is going to sit on the same horizontal plane as the hemisphere sits on. And its top, the circular rim of the top of the cylinder touches the hemisphere. Okay, let's find the radius and height of the cylinder of maximum volume. So for this one, it's good, especially this type of geometry one, it's good to start with a picture. So we have our hemisphere sitting something like this. And we know the radius of this hemisphere here is big R. And now our cylinder sits inside of this, something like this. And so let's say this thing has radius little r and height h. And we want to maximize that volume. So we know the volume of the cylinder here is pi r squared h. Now what we need to do is we need to use the fact that it's inside this sphere to relate r and h. So these are both varying, so we need a way to get rid of one of these variables so we can use what we've learned about derivatives to find the maximum here. So let's think about looking at this cylinder, the sphere and the cylinder kind of from the side here. So then my hemisphere would look like this, and this would go out to R, and this would go to R. And my cylinder would look something like this, with this R and this H. And the trick here to use is that if I draw this line straight out like this is still radius R. So what we get is we get a triangle here, where this is R, this is H, and this is little r. So that tells me then that big R squared is little r squared plus h squared. And notice in our equation up here for the volume, we have an r squared. So if we solve this thing for little r squared, I get big R squared minus little h squared. So I can plug that in, and I can rewrite this volume, which was pi r squared h, is pi, and then big R squared minus little h squared times h. And we can go ahead and FOIL this out to be pi r squared h minus pi h cubed. And now we've got a formula that we can use to find the minimum value of, or maximum value of in this case. So v prime of h is pi r squared minus 3 pi h squared. Notice this is defined everywhere, so we want to find where it's equal to 0. And so solving this for h, I have h squared is equal, the pi's cancel, and I'm going to get r squared over 3, which means h is plus or minus r over square root of 3. Of course, we want positive values here, so that means I want h is equal to r over square root of 3 is my critical number. Now let's check this gives a maximum, and then we'll go back and figure out what little r is. So if I look at the derivative here, v prime of h, if I take the derivative of this, I'm going to get minus 6 pi h. So v double prime of r over square root of 3 is minus 6 pi r over square root of 3, which is negative. So this gives a maximum. And now we need to find the value for little r as well, because it wanted both of these. So remember, this formula gave us little r, so this is square root of r squared minus r squared over 3. So this is square root of 2/3 times big R. Okay, so let's do one more example. Okay, so we've got a circular ring of radius r0 lying in a plane perpendicular to the x-axis and centered at the origin. The ring has a positive electric charge spread uniformly over it. The electric field in the x direction, call this E, at the point x on the axis is given by E of x is equal to kx over x squared plus r0 squared to the 3/2. K is bigger than 0 and is a constant. So what we're going to ask about is what value of x gives the maximum and minimum of this electric field. Okay, so just like we've been doing, we need to find the critical numbers for this. Notice that x squared plus r0 squared, that's always going to be positive. That's going to be important for us here when we take the derivative. So let's just use the quotient rule. So derivative of the top is k. And I've got to leave the bottom alone, minus the top. And if I take the derivative of the bottom, we get a 3/2 x squared plus r0 squared to the 1/2. And I need to multiply that by the derivative of what's inside, which is 2x, all over the bottom squared. And now we'd like to simplify this sum so it's easier to work with. So notice I can write this. I have k times x squared plus r0 squared to the 3/2 minus 3k x squared times x squared plus r0 squared to the 1/2 all over x squared plus r0 squared cubed. Now both terms in the top have a k and an x squared plus r0 squared to the 1/2. And if I factor that out, the first term will be left with x squared plus r0 squared. In the second term, we take everything there. We take the k and then the product there, so we just get a minus 3x squared left over. And on the bottom, I have x squared plus r0 squared cubed. Now I can simplify this a bit. I have a k, and then I'm going to have an r0 squared minus 2x squared. And then I can cancel that 1/2 off for part of the bottom, and this just becomes 5/2. So this is my derivative. Now notice, like I said before we started taking the derivative, the x0 plus r0 squared is always positive. So that means there's no points where this is undefined. So if e prime of x is equal to 0, when the top is equal to 0, so when r squared minus 2x squared is equal to 0. So that gives me when x squared is equal to 1/2 r0 squared. So x is equal to plus or minus r0 over square root of 2. And now in this case, there's no reason that we would exclude the positive or the negative part of this. So those are both critical numbers. And we have to decide whether they give maximums or minimums. So let's take the second derivative. So if we use this last form here for the derivative, we can use the quotient rule again. So the derivative of the top is going to be minus 4xk times the bottom minus the top times the derivative of the bottom. And so take a 1 away from this, and I'm going to have 3/2, and I'm going to have a minus 2x all over the bottom squared. So it's just going to be x squared plus r0 squared to the 5th. And if we simplify this a bit, this gives me k x squared plus r0 squared. And if I factor out a 3/2 from this because it's in both terms there, then I'm going to have a minus 2x x squared plus r0 squared minus 5x r0 squared minus 2x squared all over x squared plus r0 squared to the 5th. And we could simplify this further if we like, but it's not strictly necessary. So notice if I plug in, say, r0 over square root of 2, I get k, and now x, so I'm going to get r0 squared over 2 plus r0 squared to the 3/2. I'm going to get minus 2 r0 over square root of 2. r0 squared over 2 plus r0 squared minus 5 r0 over square root of 2. And then notice the second term here gives me r0 squared minus 2 r0 squared over 2. So this term actually gives 0 all over r0 squared over 2 plus r0 squared to the 5th. So notice this is k, and then from this I get a 3/2 r0 squared to the 3/2, and then I'm going to get a minus r0, or minus, say, minus square root of 2 r0, and then I get a 3/2 r0 squared. The last term is gone, and then I get 3/2 r0 squared to the 5th. So notice everything is positive here except for that negative. So this is less than 0. So less than 0 looks like this. So x equals r0 over square root of 2 gives a maximum for E. And now we can run the same thing with negative r0 over square root of 2. And so if we do that, we're going to get mostly the same things here. So I'm going to get k, and then since I'm squaring the terms for the first part, I'm still going to get r0 squared over 2 plus r0 squared to the 3/2. And then I get negative, r0 over square root of 2. And then I get the 3/2 r0 squared again, minus, and then I'll get a 0 there again, same calculation as above. And then the 3/2 r0 squared to the 5th. And so we can see in this case, I get a k, I get 3 halves r0 squared to the 3 halves. And then notice the negatives cancel this time. So I get r0 over square root of 2 times 3 halves r0 squared all over 3 halves r0 squared to the 5th. And this is bigger than 0. So x equals negative r0 squared over 2 gives a minimum for E.